for joining us again today on YouTube. Here at the university, we don't just delve into the papers, but we actually are all about research and development and practical experimentation, as well as educating and informing the public. Today, we are going to show you the purpose of the relay. As you can see here, we've selected our sample with a clear see-through housing so that you may see how it works. On this side, we have a coil, which is just a piece of metal with wire, many turns of wire wound around it. Nothing very exciting about that. The coil contacts come out here, so the current comes in at one, goes through the long turns of wire around the coil and comes back out the other end. And what happens is, when electricity passes into the coil, a magnetic field is built which pulls this arm up top here down to the core. Over here now in the other half of the relay is the mechanical part. Once the magnet is energized and it pulls down this little arm, it pushes here this contact over in this direction that I'm doing with the pen, so that this contact is broken and this one is made. We have 3 connections here, of which the only one we're interested in using is the one where it actually makes the circuit. So we're not interested in the break-in circuit, but if you need a break-in circuit, you can use these 2 contacts. However, today we are going to activate a general household fan operating on normal domestic AC supply with this contact closure, which is going to occur when power is applied to the relay coil. Now, the other interesting aspect of this device is that we can control a larger current on a higher voltage with the contacts, whereas the coil itself can be working on much lower voltage, microscopic current, and we have it in fact hooked up to a itsy bitsy little transistor. Look at the size of that transistor. This is a 2N2222A transistor in a plastic package. And I'll move away so you can see it clearly, because it is such a small piece of plastic you wouldn't even think it could handle any current or power. But it does very well. Now, this is our 12-volt supply that is going to power the transistor and the relay coil. As you can see, we have it here taken at the positive and negative terminals, and we have the meter to prove to you that we're only putting in 12.77 volts, okay? So that's all that's being applied to the circuit. Now, so the coil is going to be energized with the 12 volts, which is going to switch 120 volts on the contact to turn on your giant household fan, okay? But in the base of the transistor, we have a resistor here, 2.7K, and we are going to apply a minuscule current through the base in order to actuate the coil. Observe that when I touch the resistor, the coil closes, contact closes, and when I release, it releases. But the most interesting thing about this is the current. Observe the meter over here, where we can show that the current required to actually cause the coil to energize is only 4.4 milliamps. Isn't that amazing? A current of 4.4 milliamps we are switching to cause the coil to activate. Now, let us not tell lies. The coil itself requires more than 4.4 millivolts. That is the purpose of the transistor here. The transistor takes our little 4.4 milliamps and multiplies it into a larger current that the coil requires. So that's probably around 50 milliamps to trigger the coil. Here we have a broken domestic fan, but at least the motor is running quite satisfactorily. the cable from the fan to the plug. As you can see, we have simply cut the cable that goes to the plug, and we have inserted our relay contact and a capacitor. This orange thing across is called a capacitor. We're going to explain the reason for the capacitor. This is a very small contact, as you can see, and what would happen if we did not have the capacitor is that when the contact tries to open, sort of like pulling out the plug, you would have a spark. I'm sure you all have seen that many times. When you try to pull out a plug of a working fan, you can even see a spark at the plug sometimes, even when you plug it out or plug it in. This capacitor temporarily absorbs the energy that would normally create the spark, the inductive energy coming back from the fan. The capacitor is used to absorb it without damage so that it extends the life of the contact and prevents it from sticking. Now over there, as you can see, the fan is not spinning yet. Okay, it's not spinning because the contact is broken, as you can clearly see. See the broken contact here? Now we are going to connect the power to the little 4.4 milliamps we were talking about all this time, and it's going to cause the contact to close and the fan to spin. Okay? Fan is spinning. Now just focus on the contacts there so that you can see that they're closed, and there they are opened, and you can see the fan has ceased to operate. Okay, we're explaining our transistor circuit here for the benefit of those who might want to build it. The two resistors, this 1K resistor and this 2.7K resistor over here, they fix the base voltage, okay, provide the base with a positive voltage that allows the transistor to conduct. All I was doing in my demonstration, I was applying that power positive voltage at this end of the resistor. So when there was nothing connected to this end of the resistor, as you see right now, the base is returned to ground through the 1K resistor, and essentially the transistor does not conduct. Now, in the collector circuit of the transistor, here's the collector circuit, the coil constitutes the load. So obviously the current of the transistor flows through the coil to energize it. Now the purpose of this little device here, this is a diode, okay, this little thing here is a diode, and the circular silver band on the diode indicates the cathode. A diode is a device that only allows current to flow through in one direction. In this case, from the direction, from the lead that's connected to the silver band over to the other side. It will not flow in the reverse direction. So in actual fact, current is not flowing through this diode because we have the negative side connected to positive and the positive side connected to the collector. So in normal operation, the diode does not conduct, but rather the current from the transistor flows through the coil and comes around to the other side. The purpose of the diode comes into view when the transistor cuts off the supply of current. Once the collector is disconnected from the power as a result of the transistor turning off, then the electricity stored in the coil has nowhere to go. And what happens is it flows backwards in the reverse direction through the diode and dissipates harmlessly, preventing a problem for the transistor. So looking forward to the next episode, and tune in again and see you next time at uetube.com.